Hey everyone, and welcome to this explainer. Today, we're going to trace the absolutely fascinating evolutionary journey of the humble switch. We'll be moving all the way from clunky, sparking mechanical parts to the lightning-fast, totally invisible world of solid-state physics. It's an incredible technological leap that literally makes the modern world possible, and I'm super excited to guide you through it.
You know that light switch on your wall? It works perfectly fine for turning a bulb on and off once or twice a day. But think about it, it's a massive roadblock to technological progress if you have to rely on physical moving parts for computing. So ask yourself, how exactly do our modern devices, like that smartphone right in your pocket, manage to flip billions of switches in just one single second? You certainly can't pull that off with physical levers.
Okay, so here's our roadmap for today. We're going to cover the switching problem, mechanical and relay switches, the solid-state revolution, how transistor switches actually work, and finally, mapping out those transistor states.
Let's kick things off with Section 1, the switching problem. Basically, why did engineers need to move past physical switches in the first place? Well, a perfect switching circuit needs to do two things flawlessly. It needs to turn the electrical current on or off incredibly fast, and it needs to do it without destroying itself. When you break a live circuit mechanically, you almost always get a spark. And over time, that sparking literally burns and wears down the metal contacts. If your laptop processor relied on physical switches, it would basically act like a miniature campfire.
Moving to Section 2, mechanical and relay switches. Let's look at how we used to do things. Good old mechanical switches, like your standard tumbler switch, have a few fatal flaws for computing. First, in the closed position, the switch carries the entire load of the current, so they have to be large and heavy just to avoid overheating. Second, as we mentioned, when you break the circuit, they spark, causing massive wear and tear. And third, because they rely on physical mass, their inertia makes them incredibly slow, like way too slow for what we need.
So, as a stepping stone, engineers came up with the electromechanical relay. It's actually a pretty clever workaround. It uses a tiny power source running through a magnetic solenoid to pull a physical lever, which then safely controls a much larger power source. The operator stays safe, and the main switch doesn't spark dangerously. But, yeah, there's a catch. It still relies on a physical lever, a spring, and an armature. That means it still suffers from mechanical wear and tear, and it's still fundamentally limited by how fast a physical object can move.
Which brings us to Section 3, and really the hero of our explainer, the solid-state revolution.
Let's put these two eras of technology head-to-head. On one side, we have the electromechanical relay. Because it has moving parts, its speed is totally bottlenecked at less than 5 operations per second. On the other side, the electronic switch, using semiconductor materials. It has absolutely zero moving parts, it is completely noiseless, and it can execute a mind-blowing 10 to the power of 9 operations per second.
Let's just pause on that number for a second. 10 to the power of 9. That is 1 billion operations every single second. Going from 5 to 1 billion isn't just a nice upgrade, it's an absolute foundational requirement for modern computing. The digital age literally does not exist without that kind of speed.
By ditching physical levers for transistors, electronic switches completely rewrote the rulebook. Zero moving parts means practically zero wear and tear. They're totally silent. They are remarkably small and lightweight, small enough to pack billions of them into your computer's processor. They're cheaper to make, need basically zero maintenance since they're solid state, and of course they have that blistering speed.
All right, Section 4, how transistor switches work. How do you turn a current on and off without actually moving anything?
Well, it all comes down to controlling voltage. Now, don't let the engineering jargon intimidate you. Cutoff is simply the technical term for the off state. When the input voltage at the base of the transistor is 0 or negative enough, it throws up a barrier. No current can flow through to the collector. In this cutoff state, the transistor is doing the exact same job as a physical switch in the open or off position.
On the flip side, we have saturation, and this is just the on state. When you apply a positive enough voltage to the base, that barrier totally vanishes. The transistor saturates,
meaning the metaphorical door flies wide open and maximum current flows freely through the circuit. It behaves exactly like a tightly closed on mechanical switch.
If you align the invisible electronic logic right next to a physical switch, it really clicks. Negative voltage equals zero current, perfectly mimicking an open switch. Positive voltage equals free-flowing current, mimicking a closed switch. It's an elegant, completely invisible replacement.
Finally, let's jump into Section 5, mapping the transistor states. To really visualize what's happening, we need to map out 3 distinct zones of operation. First, you have the off region, which we called cutoff. Second, the on region, or saturation. And third, there's the active region. This is the transient, kind of unstable path that bridges the gap between off and on.
When mapping this out on an output characteristics graph, it forms a really clear picture. Down at the very bottom, where current is basically 0, there's your off condition. Then, grouped up at the top left where the current is maxed out, you find your on saturation condition. By driving the transistor back and forth between those 2 extreme points, we successfully create our binary switch. But what about that space in between? That diagonal path from the bottom right up to the top left is the active region. And here's the crucial thing. That space is completely unstable for switching. Why? Because in this transient zone, the transistor isn't acting like a binary switch at all. It operates more like a linear amplifier, where tiny input changes cause huge output fluctuations. If we want a reliable switch, we have to snap right past this active region as fast as possible, straight from off to on. Now, full disclosure, there is one tiny catch compared to our old mechanical switches. When a physical lever breaks a circuit, the current drops to absolute true zero. A solid-state switch isn't entirely perfect. In the off state, it actually lets a microscopic collector leakage current slip through because of something called minority carriers. But in modern silicon transistors, this leakage is so remarkably small that for all practical computing purposes, we just completely ignore it. So, as we wrap up this explainer on the massive leap from clunky mechanical levers to invisible solid-state physics, I really want to leave you with this final thought. You interact with this technology every single day without ever seeing it. The next time you tap your phone screen to send a text or load up a video, just ask yourself, how many billion solid-state switches just flipped back and forth between cutoff and saturation completely silently just to make that happen? It's a hidden symphony of physics, right there in the palm of your hand. Pretty amazing, right? Thanks for joining me.